And also thank you for having me today. All right, cool. So it looks like we have a good number of people here. So thank you for taking time to hear me talk. I really appreciate it. And thank you in advance for engaging with good questions and discussions, because I'm really hoping for some great discussions today. Um, so the focus of the talk is really going to be about synthetic data, LLMs. We'll also talk about some, I think, speculative applications to material science. And I really want to focus on like the idea of surprise, right? So surprising results, intuitions, and myths. But this idea that I think for everyone I've talked to about LLMs and synthetic data, for anyone who doesn't directly already work on synthetic data, I think everyone has the same kind of base intuition. Like the question that comes up is, wait, isn't that circular? Like if you train an LLM on its own generations, doesn't it sort of collapse? I think this is a very reasonable intuition. And there are setups in which case this is exactly what happens. So the kind of overarching theme of the talk is going to be like how do you avoid that, right? How do you actually get value out of training on like programmatic or synthetic data, often data that's produced by LLMs, but you actually lift the performance and it's not something that's circular. That's going to be the overarching theme. And the way it's going to be structured is that I'm basically going to flip through slides that just have like figures from different recent papers. And we'll just sort of talk about and dissect those figures and what some of the interesting takeaways are. And yeah, we'll just discuss. So that's sort of the outline. Talk about synthetic data. It's really going to be centered around just snippets from different papers, and I'll do my best to give like sufficient context so the figures like make sense when we look at them in isolation. The links to the papers will be in the slides as well. And I really want to emphasize, please like don't hold your questions to the end. I think it's much easier to discuss a figure. I'm sure we all know this, right? It's way easier to discuss a figure when you're all looking at it together. You can really dig into the details then and what the intuitions and takeaways are. So don't worry about interrupting me. Like the way I've structured this talk is that there's about, I think, a dozen slides of content. So if no one asks any questions, it will go very, very quickly. Like I could probably go through in like 20 minutes. So please ask during. It doesn't have to be about just the figures either. Like we're going to talk about sort of like the ideas surrounding it. So ask about that as well. Um, you can ask in whatever form you want. You can just unmute and talk. You can use the raise hand feature. I have the chat window open as well next to the slides. So if you just type something in the chat that's a question, do that at any point, please, and I'm happy to answer. It can just be about LLMs in general as well, whether it's synthetic data, what's directly on the slide, or just about like reasoning in LLMs. I'm happy to talk about any of those topics. Yeah. So if everyone is good with that setup, let's just get right into it. Okay. So I'll only have one slide on preliminaries because I'm sure we all have like a variety of background and familiarity and experience with LLMs. I think there's only one really important intuition to cement in, which is that regardless of how advanced LLMs are in terms of the capabilities, at least all of the current LLMs are ultimately like they're a type of next token prediction, right? Like there are auto-regressive models. So when you look at what is an LLM actually doing, if you have some example text here, like how does that actually get framed as an ML problem, right? You have some like sequence of tokens, that's like the green here as an input, and then you predict some output. Uh, obviously this can manifest in many ways, right? There's all kinds of complicated things that LLMs can do now. They can be like an agent, you can do RAG and so on. But the reason I highlight this is that all of those can also still be broken down into this fundamental framing and intuition, right? Like if we consider RAG as an example, well, you retrieve over something like some document, you put that into the prompt so that changes within the input. And so you change the conditional probability. And so you change what gets output, right? The answer becomes like grounded instead of hallucinatory, for example. Basically every advanced LLM capability that you see can somehow be worked backwards into this framing. So I just wanted to highlight that for anyone who's just new to LLMs and you want like a really quick intuitive framing for what they do, you can think of it like this. And even if you are quite advanced in your usage and research with LLMs, this is sort of a reminder that no matter what we're talking about here, we can still sort of break it down into this framing, at least intuitively. Okay, so with that preliminary out of the way, I want to talk a little bit about this kind of big question. So I think this I would call this a bit of a myth that people say that, oh, our LLM's kind of like the average of the internet. I think this idea that scrape the internet to train LLMs. And to some extent, there's some truth in that in using kind of large collections of kind of free and public web text. But there's this paper that got a lot of buzz last year, which, in all rights, I think is a great paper. And it shows this idea of if you recursively train large language models on data that they've generated, you get this kind of collapse behavior. You lose like the long tail of distribution and what they can generate, and eventually the models become worse. And what I think is quite interesting in the abstract is that they frame it as like, what happens to they use the example of a GPT-N because there's like 2, 3, 4, and so on. Like what happens when you get to like 6 or 7 or 8 when LLMs contribute text online and you kind of rescrape that and retrain on it. It's an interesting framing and one that I've heard a lot when talking to different people about either advancing the next generation of LLMs or especially in the context of synthetic data. And kind of the whole point of this talk is that I don't think this is a very realistic framing. Like no one really does this because the lift that you can get in terms of improving modern LLMs, a lot of that does not really come from sort of training on a slightly more updated version of web text. And there are many, many useful techniques that can be used to ensure that the synthetic data you're training on is actually improving the capability of a model. It's not as though you're sort of naively just sampling from a model and then training it on itself. So put another way, I think the conclusion of this paper is very valid, right? If you train a model on itself over and over again, it will kind of collapse. But I think that the reality of what people are doing is not that. So it's not really much of a realistic risk, I would say, for model development. Okay, so let's start with some motivating examples, right? I think people again have this realistic concern that synthetic data can be circular, but I just want to start with some proof points that it doesn't have to be that way. So on the left, I have a figure. This is from like a Cohere paper, and on the right, it's an NVIDIA paper on OpenMath Instruct. So let me first talk about the left figure. The point of it is that you see these two graphs. The y-axis is basically it's like accuracy or performance. These are some like evaluation benchmarks. There's one on reasoning. There's one on code. This paper happens to be about introducing code and training data. But what's interesting is like the different bars that you see on this left plot, they're like different data mixes. And the rightmost one, so the darkest orange, is a code plus synth mix. Honestly, the paper is a little bit vague, and I guess I'll also have to be vague about what that synth data is. It's a proprietary mix, but you can at least rest assured that it's like synthetic code data. And you can see that it has like an enormous boost in terms of metrics over the other settings. So the point of this is that there really is like there's genuine empirical data that shows that synthetic training data really can make models much stronger at tasks that actually matter. So like being good at writing code that works is obviously a useful task for LLMs. If anyone here's used any of like kind of code editors that have LLMs plugged in, I'm sure you tried that. It actually is kind of useful sometimes. So that's kind of one example of just quickly showing the result that we're going to work backwards from. That synthetic data really is useful and it shows up when you actually evaluate models. On the right is another quite interesting example. This is from OpenMath Instruct 2, an NVIDIA paper. And the point of this is that I think there's kind of two takeaways from this plot. So on the y-axis, you see test accuracy on this math in kind of all caps evaluation set. So it's a popular evaluation benchmark that people use for LLM mathematical capability. And on the x-axis, you see like the size of the data set. So this is sort of, I guess, it's a type of learning curve, I suppose, right? More training data, and they train at a few different data set sizes to see how much the capability improves. And they have like their open math version of a llama fine tune, and they're comparing it to sort of the official, I guess, llama 3.1 releases. And they show that with this open math instruct data set, which I should add is a completely synthetic data set, they actually exceed the performance. So I think that's one takeaway, right? That the synthetic data actually works. It actually makes the models better. In fact, can work better than other approaches that do not use synthetic data or don't use it as heavily. And what's also interesting is that the nature of the approach in some ways can only be done by synthetic data. Like if you look at the x-axis on this right side plot, I wish there were a way to do like a laser pointer. There must be, but I have to admit, I'm not that good at using, I don't usually use Zoom. Anyway, whatever. I will simply orally describe what we're seeing here. Okay, anyway, so the 14.3, right? That's where the x-axis ends on the right plot. Um, what's interesting is that that kind of result is only possible with synthetic data, right? Could you imagine like how much money and time it would take to ask humans to annotate 14 million data points? Like if you do the math with any kind of reasonable estimate, even if you imagine you had a very efficient workforce, it's just astronomical in terms of either time cost or monetary cost or both. Um, okay, and someone has pointed, thank you, that the mouse cursor is visible. I actually didn't realize that. Okay, cool, nice. I don't even need a laser pointer. So yes, this is my point here. It's not only that synthetic data works, but there are like published proof points of um, it like uniquely works, or there are some things you can do with synthetic data, namely data volume, that just aren't practical with other methods. So even if it's, for example, less efficient than human annotated data in certain cases, you can sort of make up the difference with volume because it's so cheap to produce comparatively. Um, if people here haven't used LLMs a bunch in bulk and you want like kind of a benchmark for like how much they cost to use for inference, right, to produce training data. Obviously, it depends on the model and the provider and many other factors. But I think for many reasonable models, it's like on the order of a couple of dollars per million tokens, something to that effect. So you can imagine that that's much cheaper when you compare it to like asking a human to write. I guess a million tokens maybe is like a couple 100,000 words or something like that. So the economics work out quite interestingly. Okay. So maybe I'll pause here. So this is the kind of like our first set of like, let's say actual figures of snippets from some papers. I'll pause for a moment in case anyone has any questions on these and the kind of the overall motivation of synthetic data and the fact that I mean, empirically at least it clearly works in some cases. Okay, but if no questions, I'm just gonna keep going. Okay. Wait, what? Yep. Is there a question?
Yeah. For the code plus synthetic data, how can they get that synthetic data for the code?
Oh, how do you get synthetic data for code, right? Like, sorry, you're kind of quiet at the beginning there, so just want to make sure I heard. Okay. How do you get synthetic data for code?
Yeah.
Okay. The paper this is from is a bit vague, so I'll also I don't know, I'll kind of match the level of detail. I mean, as you already know, you can ask an LLM to generate code. So basically that. And the nice thing about code is that there are formal ways you can verify it. I won't get into the specifics, but you can imagine if you want to check if your code is correct, you can ask someone to review it, but there's also other stuff you can do, right? So that is basically the approach. Yeah. And so in a way that's, I mean, depending on your existing intuitions about synthetic data, that's either surprising or unsurprising, I guess. I think probably to most people, unsurprising that you can ask an LLM to write code and then do something to make sure that code is correct, or at least as correct as you can guarantee, like to some level of correctness. But I think what might be surprising to many people is that approach is so effective. But empirically it is.
Okay, thank you.
Okay, and then there's another question in chat about like, yeah, what type of data can we produce synthetically? Like just text or scientific reason content? I would argue all of the above. In fact, I think some of the most interesting applications that I think are being done and maybe have yet to be done are on creativity in this regard of like, what can you produce synthetically? What can you verify programmatically or synthetically? And then how can you use that to bake a capability into the model? That will make more sense in the later slides, I think, what I'm saying there. But I guess the direct answer to that question is, I mean, I guess you could frame it this way. What can you ask an LLM? Like basically anything, right? To the extent of, well, is that generation useful to train on? I think that depends on how good the LLM is at that, exactly the training method you're using, and then also is there any way that you can kind of verify that generation is useful? I'll get into what I mean. Actually, this is a good slide for that. So, okay, yeah. How can you verify synthetic? There's another question in the chat. Like, how can you verify synthetic data? If there's too much data for human to verify. Great question. The answer is don't use humans. obviously you can use humans for a little bit of data. I think that that's actually a very strong method. But this, okay, this is actually the perfect slide for that question. So this is the kind of overall training, post-training diagram from the Llama 3 paper. There's a bunch of stuff in here that I think is not that important for the sake of this talk. But what is important is that you can see there's kind of like a loop. I think I phrased it as a question, but I think for the sake of time, I'll just kind of say that, they do like SFT model, right? So this is supervised fine-tune. This is like a normal thing that you do, right? You take a pre-trained base model, you give it maybe like instruction prompts, right? So maybe the prompt is a question and the completion is like an answer to the question. And that's how you get like those AI assistant chatbots. But you can trace that there's like a loop where it's like you keep training the model, and you kind of get the best models, and then you generate more from that model, and you do something called rejection sampling, and you train it again. So if you kind of follow the logic of that, that means you actually are taking the models, generating more like answers or completions from them, and training on them again. And so the question is, well, like how is that not circular? And the answer is you can use like a reward model to rank them. There's many different ways you can implement a reward model, but for the sake of this, and I think in principle, all you really need for this to work is just have any function, whether that function is like a neural net or something else, any function that ranks completions like better to worse. And you can use that in this kind of setup. If you wanted intuition on like why is this not circular, you can imagine that, well, because when you ask an LLM to like get a completion or to answer a question or so on, it's like probabilistic sampling, right? So as long as you don't have a zero temperature, you'll get different answers. And then if you rank them, you can choose which ones are better by some metric. And so in a sense, you can kind of sharpen the distribution that you are learning, right? You can imagine that if your initial LLM has some distribution over answers, and then if you sample many, many times, and you sub-select the answers that you're going to keep training on and train on those again, you can like narrow the distribution. And if you're smart about your ranking over time and over iterations, that distribution will be better for whatever purpose that you're trying to achieve. So some examples of better might be like more correct, right? Let's say if you're using code or math or something like that, or it could be, let's say you want an LLM that's good at writing essays. Maybe better is just longer, right? There are some kind of trivial examples of better. So when I say verification here, verification doesn't have to mean like necessarily correct or incorrect. It can just mean better than another alternative. So this is one way you can avoid things being circular. So there's a question here about clarifying the reward model. Is it used to get scores for the rejections? Yes. Scores, there's multiple ways to implement it. I think so. The most common, I think, would be like scoring a completion. So given a prompt of completion, score it. You can also be given a pair of completions and then rank better or worse, or how much better or worse. So it still is a score, but like pairwise score. I think this is the most common. Maybe like the other common one is that actually the reward model is also an LLM, and you like literally ask it with like a rubric or something, like rank this completion to this rubric, like score out of 5. That works too. Yeah, I think those are the most common implementations. But you can think of it as a score. I think that's the most correct, like abstracted way to think of it. Okay, and have there ever been physical demonstrations of synthetic data? That's another question here. I'm not sure if I'm interpreting this question correctly. So physical demonstrations can mean, could the data be like tied to some real physical source? I'm almost certain, yeah. So I think the problem then is that like, is it still synthetic? You know what I mean? It's like let's say you had a robotic lab setup or something like that, and you get data from there. I would say that data is physical, but then is it still synthetic? It's like programmatic, I guess, but it's kind of real. So I don't know if you'd call it synthetic. Anyway, I have, I've definitely seen papers where people connect LLMs to robots as kind of like the main thing, whether that's a robotic arm in a lab setup or just like a different kind of robot. One of the disadvantages there, though, is that your data volume doesn't scale as trivially as it does for when it's just like, let's say you're hooking it up to like a Python environment or something, right? You could scale that like very, very, very easily in a way that you can't with a robot that's like bound by physical reality. Okay. Hopefully I've answered that question, but feel free to ask like another version of it if I didn't really answer it. Okay, there's another question in the chat. So when generating synthetic data, for training or fine-tuning LLMs? How does the format and quality of the data impact the model's performance? Okay, well, that's so interesting. Okay, so a lot, but there's exceptions. There's actually going to be a slide on that in a bit. So a lot, but there are exceptions. Specifically, should we use more casual, diverse language to capture rare linguistic patterns, or should we prioritize well-formatted language? Oh man, I would actually say it depends. It depends. I think in general, diversity matters, and I think, and I mean here I mean diversity in the most literal sense, diversity in the data, like n-gram diversity. You do not want memorization over like the same strings basically, because that's a really easy way for things to actually start kind of collapsing. So like data diversity in like the literal sense of like characters and strings, that matters a lot. Whether linguistic patterns matters, I think heavily depends on what you're using your LLM for, right? If it's like a general purpose LLM you're deploying to anyone, you're like an LLM company, then yeah, I guess it matters a lot. If you're using it for, to control a RAG system or like an agent, like function calling system for like a robotic lab, like probably doesn't matter that much, right? Maybe all it's ever going to output is like JSON payloads to call an API. Then it probably doesn't matter. So I don't think there's like an all-encompassing answer. Okay, and one more question in the chat. How do we address noise generated along with useful data? Prompt engineering or another evaluate. Okay. I'm going to reverse this question because noise generated with useful data. I assume this is about non-zero temperature sampling, right? It's like when you sample an LLM a bunch of times to do something like training it on those completions or doing rejection sampling. It's like some of those completions will be great, and some of them will suck. But how do you distinguish between a noise and useful data? I would argue that that's like baked into your reward model or your ranking function or something. Right? I think intrinsically it's actually hard to say what is noise and what is useful data, because until you rank it or decide what you care about in terms of the LLM's capability, I think fundamentally there's no difference between those completions. Yeah, so I think it's non-trivial to say what's noise and what isn't. I think like the variety of the sampling you get is actually part of what makes it useful, right? If you sampled and got like extremely narrow distributions, then you kind of, in a sense, couldn't escape that distribution, right? The ability to sort of explore, if you think about this in kind of like an active learning sense, maybe, like the ability to explore is part of what makes the setup useful. Okay, what needs to be considered when combining synthetic and real data for fine-tuning LLM? Probably the biggest one is the difference in data volume. It's much easier to have a very, very large synthetic data set than a real data set. So if you naively combine them, you might, like one might just dwarf the other. So like the trivial thing, like the trivial answers to this is like, oh, like be careful about oversampling or subsampling, depending on how you want to do it, like balance your data set. There's a trivial answer to it. I think the more subtle answer is probably like something like style clash. So I'll give an example. Let's say, let's see here. Okay, let's say you're training an LLM, and let's say it's like for material science, right? So let's say it is like a property predictor based on descriptions of material. And you have a real world data set that you've already verified some other way. Maybe humans wrote it, and they reference like some knowledge base. And so you have data set A that's like, human verified and human written. And you have data set B that is, let's say, synthetic, right? You have a bunch of LLM completions, and you're hoping that you like filter them somehow, and you're hoping that by training on those two, you get the best of both worlds. But something that can actually happen sometimes is like, what if there's a style difference in the prompts, for example, of the synthetic prompts and the human prompts? If you forget all of the LLM and all of the, like the exact like material science example for a second, just think of it as conditional probabilities, right? Like what happens if some of your data is like bifurcated? That's basically what you're doing, right? It's like if some of them have this like particular style in the prompt, maybe they always start with like the same substring, and those are all the synthetic ones, and some of them have some different kind of signature to them. What you can actually cause the models to do is basically to like memorize the two different data sets differently. And you kind of end up training two models that are kind of hidden into one model. And so let's say you ask it about some materials, it basically has the capability to learn from the synthetic data. And for other materials, it may have the capability to learn from the human data. So kind of wrapping that into sort of an answer for what needs to be considered, I would say when you're combining synthetic or real data sets, and frankly, when you're combining any data sets, if there's like a trivial way to divide them, that can cause an LLM being trained on them to not actually like mix the learning or the capabilities. It just sort of learns them separately in a sense. And I think this danger is much more common with synthetic plus human annotated data because they just often happen to have like memorizable signatures that maybe aren't always obvious to human, but could be very exploitable by an LLM. Okay, let me just go to the next slide because I think it answers one of the previous questions. I think there was an earlier question about like, okay, but how much does like quality and formatting matter? So obviously, like your mileage may vary, but I think one of the really surprising results in this Open Math Instruct 2 paper. So this is the same one that had like the llama fine tune, I guess, comparison and like had like 14 million tokens. So on these plots, it shows again the same math a benchmark, the accuracy on the y-axis, and then on the x-axis is the size of the data set again, and the two settings, so like the A plot and the B plot, are sort of two different ways of making the data bad, basically, right? So like reducing the data quality. On the A plot, it's like wrong answer solutions. And then on the B plot, it's like you shuffle the solutions, right? So if you shuffle a solution with a different question and it's sufficiently large data set, you're like basically guaranteed it's wrong. Okay, this is the really crazy thing though. If you look at the legend, look at how much of it is incorrect, and then look at the traces. And then it's like basically it's only bad when it's like overwhelming majority incorrect. If you fine tune an LLM on even a quite appreciable portion of wrong solutions, even when it's wrong to the degree of like the solution isn't even to the right question, it still makes the model better at the in-domain task. Now, granted, right, like if you look at the size of the data set, it starts at 64K and it goes up to like 1024K. That's a weird way to write that, but anyway, 1024K. So it's like reasonably big, but I think this is like quite interesting in terms of implications for example, material science, right? Like you can imagine, I think the base intuition, where if you were making an LLM for material science, is that you should do like a bunch of validation and filtering to make sure if you're doing like some kind of prediction. For example, let's say you do like a chain of thought and then property prediction, that somehow validating that matters a lot. But maybe it doesn't, right? It's like the implication here, like for math problems where they are doing chain of thought and like a final answer. So if you ever looked at this math eval set, it's like kind of, I think, a range of sort of like high school to undergrad kind of math problems. And if you have a whole bunch of them, it sort of outweighs quality, which is, I think, quite an unintuitive result. The best intuitions I've heard on this is that when you do kind of LLM fine tuning, what it actually imparts is more about the problem solving method and kind of learning those versus specifically matching correct answers to certain problems. And I would say this empirical result seems to support that a bit. So I'll pause there if there's any questions on this, but I personally found this quite an interesting result in this paper. What is the confidence interval? Oh man. So the real answer is I'd have to double check the paper to be 100% sure. That's such a good question though. Like I'm pretty sure it's got to be like multiple training runs though. So it's either multiple training runs or multiple eval runs. Usually when you see these kind of confidence intervals in an LLM paper on an eval, there's a few sources of uncertainty. If you rerun the training, then of course there's uncertainty from like the training trajectory, right? Like you're doing this like long run optimization, you'll get a different model at the end. People often will do this by they literally rerun the training. That's very expensive. You can do different checkpoints, right, or different steps. That's less expensive, but then kind of arguable is really the same model if it's trained for different times. It could also just be evaluation uncertainty. Even when you run the eval, it's not deterministic because of one, you might not be sampling at zero temperature. Two, even if you are, the eval might come from a model, right? Like sometimes when people run these evals, there might be like, let's say the correct answer for an eval problem is like 2. And then, okay, that's just too simple. It's an example. Let's say it's like, I don't know, 3 root 2 or something like that, right? And then the LLM gets to an answer that's algebraically equivalent. It's like, how are you supposed to evaluate those? Because they're not string matches. So you could do like some symbolic solver. You could ask another LLM. Depending on the eval, they often have different setups, which means that running the eval itself is a little bit noisy. So those are, I think, reasonable answers to what the confidence intervals might be. But my honest answer is I don't remember. So check the paper. Cool. Okay, let's keep going. All right. So, oh yeah, okay. So I also want to talk about this idea of self-play. So, we've talked about kind of avoiding the circular loop of doing synthetic data that way, but yeah, there's also self-play from reinforcement learning. So it it's gotten a lot of, I think, attention in the media recently because of the R1 paper that came out, and I think also the Kimi 1.5 paper came out at the same time. But for whatever reason, I think R1 gets a lot more media attention. Um, but the idea of self-play and like great performance through that is not new, right? Of course, this is rumored what O1 did as well, and the paper that I'm linking here, this is like the Alpha Zero paper, and this is from what, like, yeah, like 2018. Um, even the like AlphaGo and such before this, I think they used like self play as well. But this is like pure self play, right? I think my best recollection, the conclusion of this paper is basically that you don't even need to train on like human grandmasters and so on, right? You can just play all these games and become superhuman in terms of your ability at the games by just doing self play and reinforcement learning. So I think this has been a known result for a while, but I think the reason why people didn't immediately try this is because in a game, there's an extremely constrained set of actions and set of rules. Okay, maybe a constrained set of actions is unfair because like Go, for example, has a huge action space. But when I say constrained, I mean like we can compute precisely what it is, even if it's large. And also the rules and reward are very constrained and well defined, right? It's obvious what it means to win a game of chess or win a game of Go. Actually, I've never played shogi, but I assume it's similar to there too. Um, and that's not just like not the same in language, right? Like, what does it mean to like win a sentence or a paragraph? I think that's kind of ill defined, and so I think it hasn't been popular until somewhat recently. But of course, it turns out that in some cases it works here as well. So this is from the R1 paper, and again here you see on the y-axis there's like accuracy. This is another like kind of really hard math competition challenge. American Invitational or something. So yeah, really hard math contest. It's basically what it is. Um, and these are like RL training steps. Um, yeah, and so they start from a base model and they just do reinforcement learning. And what's interesting is that the reward signal is basically just like, did you get the correct answer or not? So it's in a way much like the kind of chess game or Go like setup. It's just like, did you win the game or not? This is like, did you get the correct answer or not? Like, of course, there's many subtleties of like getting this to work. There's many ways it can go wrong. But I think what's interesting is that, okay, even though this is like language, which we think of as a not well defined or not well constrained domain, there are certain, I guess, subdomains within it that actually are quite verifiable. I mean, these are math problems that have a correct answer, and you really can't get better by self play and exploration, which is, I think, again, quite an interesting result. Um, it actually comes from, I think it kind of links back to this question that was asked in the chat earlier of like, how do you distinguish between like noise and good question and like good completions? It's like, yeah, I would argue in a way there isn't really distinction, right? It's like like to get this result in this figure, you have to generate many completions over many steps. And so you can imagine that there's tons of completions that are wrong, but occasionally you land on something that's good and then you learn from that and then you become better and better. Cool. Okay. Okay, so this is a little bit aside from synthetic data, but I kind of want to include it anyway because I think it's interesting and again, a surprising intuition and surprising result. And it is related because everything we've talked about synthetic data so far kind of revolves around this idea of like being able to rank completions or do some kind of formal verification. And I think all the papers I showed talk about very narrow domains, mostly math. And I think a lot of it would work for material science as well. I think you could argue that there are some material science problems that you can phrase where it starts to look a lot like a math word problem. And so you could assume, okay, yeah, maybe the same techniques would kind of work. But I think then the reasonable follow-up question is generalization, right? It's like, let's say you train an LLM, we already know they can be really good at math because of these papers that we're talking about. I think we can reasonably intuit that you could do the same for material science. It'd be a matter of changing the prompts, but assuming you have prompts that have like definitely correct answers, you can apply a lot of the same techniques. But there's kind of two generalization questions, right? Like one is like, is a model that's good, let's say material science problems, is it good at anything else? like weather and material science or anything else. I think that's a bit of an open question, to be honest. I think it would depend heavily on your training methodology. You could probably train a version where you like really overfit on the material science stuff and it loses all the other capabilities. But if you only use it for material science, that might be fine. Um, but there may be cases where you want to like somehow preserve the model's other capabilities, or you could train, for example, a model that like um, let's say predicts different kinds of properties for different classes of materials, but you find that for whatever reason it's hard to train that model all at once, and you want to all end up with a model that is really good at predicting properties of, let's say, like, inorganic solids, but then also polymers or something like that, even though those are quite different material classes. So what's interesting is you can do something called model merging. So of course, there are many ways to combine capabilities of models, but I think this is one that's kind of unintuitive. So they snippet from this paper, and this is also a Cohere paper, which is kind of nice here, is like, suppose you have task A and task B. I mean, this is like classic Pareto trade-off. So I feel like it's funny. This is like not a material science paper this is from, but it's like, I think, familiar to anyone in material science, right? So you have two different capabilities trying to optimize, and you're like, oh man, I can only get good at one of them basically, or bad at both of them. Classic trade-off. But what's interesting is that you can like merge models. And if you are not familiar with model merging, it sounds fancy, but it's like, yeah, dead simple. It's crazy. So you imagine you have like a fixed model architecture, right? So at the end of the day, it's like a set of weights, set of matrices. You train it on some data. But let's say you train like two different versions. Let's say one you train on like polymer data and one you train on, I don't know, like ceramics data. To merge those two models, typically just means like averaging the weights together. Obviously, there's many different things you can do, right? Like there's more than one way to average things. You don't have to average everything. There's like plenty of variations on this, but on the whole, yeah, you average them together in some way. And what's interesting is that you can actually retain the performance, right? So it's like, if you look at this right side of the figure, before you had models that were just good at one thing at best, you can't be good at both things for whatever reason, but when you merge them, you can actually retain the performance of both. Occasionally, you can exceed the performance. So I think that's kind of an unintuitive result. It feels like, kind of having your cake and eating it too. It seems kind of unintuitive. I looked around a bit at the literature. I couldn't find any consensus on why this works. The best intuitions that I've read and heard about is that if you consider LLMs as being very overparameterized, and I think there's good evidence of that, right? You can distill an LLM into a smaller one and retain a huge amount of performance that suggests that a lot of the parameters are maybe somehow redundant or like degenerate parameters. And if you train a model at different things, perhaps by circumstance, you're largely using different parameters. So you merge them and then they kind of don't clash with each other. Obviously, that's extremely hand wavy. And as far as I know, it's like an area of open research. But it is kind of interesting that when you merge models, you can actually do like much better than I would say like classic Pareto trade-off, which is quite interesting and I think quite relevant because it often turns out that synthetic data is very opportunistic and where it works well. But because you can kind of retain that capability and combine it with other areas, that can prove quite handy. Okay. Let's go to one more. So again, just continuing on this theme where we're looking at, different ways you can use synthetic data, different ways you can avoid this sort of circular training problem. And a really interesting one. So again, this is also from a Cohere paper, this idea of arbitrage. So it comes up in this case for multilingual arbitrage. So if you've heard about model distillation, I think people often see it in this scenario where it's like you have a big, really smart model, and there's different ways to distill. But let's say you're doing data distillation, you generate from it, so that's synthetic data, and you train a much smaller model on this generation, so it can kind of mimic the bigger model. That's like a very common setup, and I mean that works. It's useful. I think often people do this because they want a very small model. Maybe you're doing an edge deployment, deploying on a phone or something, right? Those are all like very reasonable setups. But then the fundamental problem with that is that there's kind of a ceiling of performance, right? It's like, well, you're never going to get as good as the big model was. You're just going to have some like lossy approximation or compression of it. And so the natural question is like, can you do any better? And so this is one way we can do better. The idea is that instead of just having like one big model, you have like a pool or like a bunch of big models that are good at different things. So that's what all these symbols are here, right? This is like this. I guess the symbols are different tech companies that have different LLMs, right? So you have a bunch of different like teacher models, and for different kinds of prompt distributions. So in this case, it's about multilingual training, but you can imagine it could be about a lot of things, right? If you cared about if we're doing some of this for material science, it might be like models that are really good at like core mathematics, some that are better like physics problems, some that are better like some that are like specific material science fine tunes to already to be able to do property prediction. You can imagine having a pool of those teachers and you route certain prompts or certain domains, certain capabilities to those, and then distill all of them. So you can imagine that like if you're trying to visualize this in your head, it's like each of these different teacher models has some different distribution of capability over the different domain areas. And you're like smartly sampling kind of the peaks of all of them so that your small model is still a lossy compression, but it's like this like merged compression of all these different teacher models. So it's much better than it would be if you just distilled from like one model. Yeah, so I think this is quite an interesting concept because again, it's like published in this paper in the context of multilingual, but I think it has quite interesting applications for yeah, I would say for material science, right? Just like you can just imagine that you can basically take the models that are published recently on like using LLMs for material science and are fine-tuned, and they combine that with like all the other existing general big LLMs, and it's just distill from all of them. In principle, you might end up with a very, very strong small model that actually just has the best of all the worlds. I've not seen this tried, but yeah, I don't know. In principle, it might work. Okay, so that was all of like everything up till now. So I'm kind of on the last two slides. We're basically about covering some really interesting advances from like recent papers. I think all the papers I showed were like published in the last year. That's I think that's the other thing interesting about LLMs is that um, yeah, the field moves super fast. Like I remember when I was assembling this talk, I was looking at the Llama 2 paper and I ended up not using any figures from it because it's like outdated, even though it's from 2023, because the Llama 3 paper is out. And frankly, even some stuff from that is also outdated because yeah, because there are more recent papers in 2024. So it's kind of crazy. Um, so this slide and the next slide are about more about speculation, right? Like so I welcome any discussion and questions at this point. Otherwise, I'm just going to ramble about like what I think is interesting to work on. So let me look. I think there's a question in the chat. Okay, how much magic is contained in smartly sampling the teacher models? Is it as simple as having the trainable weights in the router model? Yes, I'm trying to remember exactly what the paper does. There's even simpler heuristics that are actually pretty good. Like I think like the second best thing in the paper, if I'm remembering right, is just you look at the benchmarks for all the teacher models and just like pick like, oh, like prompts in this capability go to the teacher model that's best at this, right? So kind of like static routing. Even static routing is like way better than just distilling from one model. You can do better with some kind of opportunistic sampling, but I'm trying to remember. I think it's done with like a reward model or something. Actually, yeah, I think that is it. So I think the setup in the paper is that works the best. It's something like for any given prompt, sample from all of the models in the pool, and then use a reward model to rank what's the best completion, and then reserve that one for training. And so I guess it's the kind of like yeah dynamic routing for each prompt. It's very expensive to do it that way, right? Because if your pool is n models, I mean for each prompt you must pay for like n completions. Um, so there's some intermediate you can imagine of interpolation of like just static routing and dynamic routing depending on cost optimization if you care about that. Yeah. So but I would say concretely, most of the magic isn't just having more than one teacher model. I would say that's kind of the conclusion of that paper. That go back. Yeah, this paper. Like most of the magic is just have the pool at all. Even static routing is way better than just having one teacher. Okay, so yeah, can material science be learned by self-play? The basic idea here is that if materials project is one example, but there's plenty of materials like database property databases out there. I mean, those are like you could think of that as a something analogous to like these math contests that are floating out there in the math evaluations, right? You have like a prompt with like a correct mathematical final answer. I mean, you have materials with like, I mean, I guess air quotes correct, right? Like whatever, depending on the database, look at what do you consider for correctness, whether it's computational ab initio correctness or empirical experimental correctness, whatever. The point is that could those same techniques being used for synthetic data like work for LLMs? And I think most people, when they hear this, like the immediate thought, and I think is a reasonable thought, is like, wait, why would you use an LLM for that, right? You can already use cheap existing ML models to do this and like kind of approximate this result with much less compute. True, and I would agree with that. But if you remember the point about the capability merging and the fact that LLMs are also general models, it might be useful to have an LLM that can basically like, predict properties of materials and do RAG and make function calls to some arbitrary API and do question answering, right? Like I think what's interesting about this is that you can somehow bake these capabilities and domain knowledge into these models while retaining their general capability to just like talk with, for example. So as a made up example on the fly, because this is like the other thing on the bottom here is the SDLs from the Acceleration Consortium. It's like, imagine you had some like SDL assistant where it's like a question answer chatbot. You can ask it like, oh, how do I set this equipment? Like, what's the documentation for like, setting these two OEM parts together? I think that's the kind of thing that I've seen a lot of people starting to use LLMs like plus robotics and plus SDLs with. But what if you could also ask it like, okay, also, by the way, here's like a SIF for this material and now predict some property about it. And the same LLM could also do that. Like, I think that would be quite interesting. And I've not seen that type of approach yet. Okay, I see one more question in the chat. The oracles were not good enough. Could something similar to AWS be applied? So like having weak learners, but then use weights so they infer, and then do a strong predictor. Okay, so yeah, it's like weak learner ensemble or something. Yes, so basically soft oracles, right? Or like fuzzy oracles. Yeah, I've seen that work. You could argue that the reward model itself is kind of a fuzzy oracle, right? Like the reward model is some other learned neural net. Often it's just an LLM that you're prompting that also works for a reward model, and that's fuzzy. In many cases, empirically seems to work. But obviously the devil's in the details, right? Like how fuzzy can it be? How much data volume do you need to make up for the fuzziness? I think those are open questions. But honestly, if you look at the Open Math and Struct paper, it gives you some pretty reasonable starting heuristics. Specifically in that, like, as long as the majority of your data is correct, and also if you're on like the high tens of thousands to 100,000s, ideally millions of data points, that's like a pretty reasonable starting point. I think this is the last slide. 3 minutes left. Okay. I thought this is an interesting paper. So this is another recent one that talks. So okay, so like don't worry about the whole figure. There's like a bunch of stuff here. So I'd say like don't worry about reading it. The point is there's an LLM here. It's like an agent LLM, right? So even though there's a prompt and an output, it's accessing all this stuff. There's a retrieve, like just look at the colored boxes. There's like a retriever, there's some tools, so it's doing function calling, there's a knowledge base, it's just querying. But the point of showing this is that, okay, so like I thought this paper was cool. But what's interesting is at the end, it's just air quotes doing RAG, right? It's doing like grounded question answering. What I think is the most, so I will end with this thought, like, in my opinion, the most interesting application of LLMs in material science is not so much about RAG and answering questions more accurately, because I would argue we kind of already have that, not in natural language, but we kind of already have that, right? Like in terms of predictive models and so on. I think the most interesting is letting the LLM like call functions to do stuff in the real world. Like what if this tool hub was actually like the motors in a robotic arm? What if it was the choice of precursor you do next? What if it like controls the temperature and the controls the temperature and time settings and some like synthesis, like crystallization setup you have going on. I mean, I'm sure like at the beginning it'd be terrible, but I think that it's a much more interesting optimization space to see if we can get gains over what the current status quo is. Okay, cool. That's pretty much all I had. I guess we have like 30 seconds for one more question if anyone has any. But otherwise, I really appreciate all the questions throughout. It's been a great discussion. Yeah, cool. I think we're pretty much right on time, right? Yeah, thank you everyone, and thanks for having me.
Thank you so much, Dr. Eddie, and thanks, Dr. Eddie, for this wonderful talk. And we are right on time, so yeah, we can end the meeting and have a great day, guys.
Cool. Thanks, everyone. Have a good weekend.